Okay, now example 6, determine a differentiable function. Find dy dx implicitly for the equation sine of y equals x. Then find the largest interval in the form of, the y-axis, what number, positive and negative, around the y-axis on which this y is a differentiable function of x. And it says see figure 2.31. So first, what does the graph look like? Y, or sine of y equals x. Well, y equals the sine of x would just be a sine wave going this way. So we reverse the variables. Now we sort of have a sine wave going down the y-axis. And they're asking us the largest interval for which it would be a differentiable function. Or how could we chop that graph off so it would pass the vertical line test? Well, let's see here. We're going to fail the vertical line test at either of these two red lines because of, these points. If we want to focus around the origin, where can we chop off the function to make sure it's going to pass the vertical line test? So if you tilt your head 90 degrees in either direction, clockwise or counterclockwise, we're going to go from one peak or valley to the next peak or valley. If we chop off the function, so this red piece, it is all that is left, and we only focus on the y-axis between these 2 points, we are going to have a differentiable function, and also one that would, pass that vertical line test. So what form is it? From negative what number to its positive counterpart can we have a y value? Well, that would be from a half pi to negative a half pi. So let's start working on this, and I don't want to erase much as I go through with this because I am going to be referring back to other parts. So let's see. We're going to start with the function they gave us. The sine of y is equal to x. Find dy dx implicitly of this function. So let's take the derivative of both sides. The derivative of sine y with respect to x. So we derive sine, that's cosine of the same y, and then because the variables did not match, we would have a dy dx created by the chain rule. And that's equal to the derivative of x is 1, variables match, so we're good to go there. And to solve for dy dx equals 1 over the cosine of y. So now, since we derived with respect to x, is there a way, could we replace this cosine of y with something to make it in terms of x? And for here, we're just going to have to jump back. I'll switch over to blue to Pythagorean identity. Sine squared of something plus cosine squared of the same something is equal to 1. We're used to seeing that with x's in it from pre-calc, but we could throw y's in there also. And let's solve this for cosine squared, or cosine. So the first step is to subtract that sine squared from each side. And then we're going to take the square root of each side. Square root. So now we have the cos of y is equal to this radical. And we can leave off the pluses and minuses. If we think back from the picture, what interval are we focusing in on? From negative half pi to positive half pi. Plus or minus half pi. If we think back to the cosine function would start at a peak and go down and this way, and here is negative pi over 2, and here is positive pi over 2. So by itself, the cosine function from our given starting point, negative half pi, to our given endpoint, positive half pi, the cosine wave here is always positive. So we don't need the plus or minus. We can just focus in on that positive part. So we now have cosine of y written as something else. So let's plug that in. Oops. Ooh, I'm getting ahead of myself here. Sine of y is equal to x. Well, here we have a sine squared of y. So we can take this x and plug it in for sine. So now we have the cosine of y equals the square root of 1 minus x squared. Oops, make that look a little better there. So we just did a substitution. In place of that sine, plug in an x. Now we have this cosine of y, and we have this cosine of y, so we can substitute. Again, this radical will now go here in place of this cosine. And we have dy dx, the derivative of the original function with respect to x is 1 over the radical 1 minus x squared. So there is our derivative, dy dx, written all in terms of x. Okay, with implicit differentiation, the form of the derivative often has to be, or can be, simplified, as seen in the previous example, by the appropriate use of the original equation. So as you're working through problems like this, always have that original equation up there, maybe underline it, and look for opportunities to use that original equation as a substitution later on in the problem. A similar technique can be used to find and simplify higher order derivatives that we obtain implicitly. Here in example 7, we're going to find a second derivative implicitly. And again, we're going to always want to keep thinking, where can I use my original equation as a substitution later on in the problem? So we want here the second derivative. So let's start out with the first. So our x squared plus y squared equals 25. We take that derivative with respect to x. That's going to be 2x plus 2y dy dx equals the derivative of that constant 25 is 0, and we're going to solve for dy dx. So we're going to subtract that 2x from each side. So now over here it is a negative 2x, and we can divide through by 2y. So dy dx is equal to negative 2x divided by 2y. And that would also be a divide through by a positive 2y, and those 2's will cancel, so our derivative, dy dx, is equal to negative x divided by y. And the directions here say evaluate the first and second derivatives at the point negative 3, 4. So we found our first derivative. Let's evaluate that point there. I'll switch over to blue. As we plug in the numbers they gave us, x was negative 3, y was positive 4, and the negative will cancel into a positive. So at the point 3, 4, our derivative, our slope, our rate of change, our dy dx is positive 3/4. So now let's work on the second derivative. I'll come over here, maybe line this off. Look at our second derivative. So our first derivative, dy dx, was negative x over y. So we want to take the derivative of this derivative. So it's going to be quotient rule. Our upper derivative, the derivative of x, is 1, and the derivative of y is dy dx. So, and this negative out here, that's just a constant multiple negative 1, so we're going to have our negative outside, and in the brackets we will do the quotient rule. Low d high, y times 1 is y, minus high d low, x times dy dx, all divided by low low. Low is y, and we square it, and we close off our brackets. So remember, we're always looking to do a substitution. Can we plug anything in anywhere? Here is a dy dx. Dy dx, we said, was equal to this. So we can plug that in its place. I'm going to keep my negative outside the brackets. So now it's y minus x times, replace dy dx with our negative x over y. And then we still have our low, low down on the bottom. So let's see what happens here. Continue working in those brackets. We have our negative. Our numerator is y. Minus and minus are going to combine into a plus. And then we'll have x squared over y, all divided by y squared. Okay, I don't want to erase what I have here on this side, but we'll go right here. We have a fraction within a fraction, a numerator or a fraction just within the numerator of what we have here in the brackets. How do we eliminate those fractions? Let's multiply the numerator through by y, and let's multiply the denominator by the same y to make it fair. That will eliminate this denominator. So we still have a negative out front. Distribute the y. y times y is y squared. Y hits this term and cancels out the y in the bottom, so we're just left with the numerator, plus x squared. All divided by y times y squared is now y to the third. Can you see another substitution? Back to the original problem, underlined in the upper left in black, x squared plus y squared equals 25 in this problem. Here's x squared plus y squared. Replace that with a 25. So we have negative, that numerator becomes a 25 over y to the third. This is our second derivative, d squared y over dx squared. And again, they wanted us to evaluate the first and second derivatives at this point. Now with the substitutions we've made, our second derivative no longer even has an x in it anywhere. So we have our negative 25 over, that's an ugly 5, I can't let that stand, negative 25 over y to the third. Well, our y value is 4. 4 to the third is 64. So our second derivative, our rate of change of our rate of change at that given point, is negative 25/64. And here we did do two different substitutions. We took our original dy dx and we plugged it into the problem as we were working on the second derivative, and then just a little bit later we took our original equation and plugged it back in there to simplify things down even further. Lots of fun in calculus. Example 8. Find the tangent line to the graph of this mess, x squared times the quantity x squared plus y squared equals y squared, at this point, root 2 over 2, comma, root 2 over 2, as shown in the figure. So here what we have are two parabolas touching at the origin, one opening up, one opening down. A complicated function, draws this graph, and we want to find the tangent line to the graph. So now they're not just asking us for a slope, they're asking us to actually find the tangent line. And that's better. The worst thing is when they say find the derivative at this point, they want you to actually have the explicit and simplified derivative at a point. So this, it might not be too bad. And even now that I think about it, maybe we will go all the way and find that explicit derivative. Instead of, here's another problem, we want the tangent line. And to find the tangent line, we need the slope, m equals something, and we need a point on the graph. And we have that point on the graph, root 2 over 2, root 2 over 2. So all we really need to find the equation of this tangent line is the slope. And we could just take the implicit derivative, immediately plug in our given point, and find that slope. Just for fun in this problem, we are going to find that derivative. We are going to simplify down and solve for dy dx, because we did skip it on that other problem, and actually that other problem was much, much worse. So let's see here. Our original equation is x squared times the quantity x squared plus y squared equals y squared. How should we start this problem? When we look on the left here, we have something times a something, so we could do the product rule here, first times derivative second, second times the derivative of the first, blah, blah, blah. That could get a little messy. So, since we have this implicit differentiation tactic now, let's see what would happen if we distribute this x squared. X squared times x squared is x to the fourth, plus now x squared times y squared will give us x squared times y squared. That will be a product rule, but it'll be a much easier product rule than what we would encounter, trying it on the original part of the equation. Now that's equal to y squared. Okay, I don't know how much room I'm going to need, but I will slide a little bit of this up so I have a little more room to work. Because now let's take the derivative with respect to x. So first term, easy one, 4x to the third plus. Now we are going to have a product rule. And let me work up this way. Derivative of that term will be a 2x. The derivative here will be a 2y. And instead of dy dx, let's use prime notation, y prime. We'll change it up a little bit. And that's easier to work with when we're isolating that variable at the end. So, product rule. First times the derivative of the second. Our first is x squared times the derivative of the second is 2y, y prime, plus the second, y squared, times the derivative of the first, 2x. So we got the left side all done, and that is equal to, derivative here with respect to x is 2y, y prime. Alright, now we want to get any term with a y prime on the left side. So this term has a y prime, it's already on the left, it'll stay. This term has a y prime. It's going to have to be moved over here to the left. Anything without a y prime will be moved to the right. So here on the left side, we're going to start with our x squared times 2y times y prime. And then this term is positive on the right side of the equals. It's going to jump over. Now it's going to become a negative 2y, y prime. And then we have our equal sign, so these terms are in their proper places. Now we have our equals. Both of these terms, I'll underline in black, are now going to move to the other side and become negative. So we're going to have our negative 4x to the third minus 2 x y squared. X y squared. And then we want to factor out the y prime. Let's see here. I guess we can go through, every coefficient here is divisible by 2. So let's just get these coefficients cleaned up. You know, that 2 will divide out to a 1, that'll divide out to a 1. This will divide out to a 2, and then this one will also divide out. And now on the left side, we can factor out the y prime. Y prime is pulled out, so we have the y primes are factored out. What's left in the parentheses? We have an x squared y minus y. And then over here on the other side, I guess we can factor out an x. We can factor out an x. So then we're left with what inside? Negative 2x squared minus y squared. Okay, and I guess I can erase this. I did miss, it looks like there on the left side also we can factor out another y, but I guess we'll do that after we do a little division here. So to isolate y prime equals, we're going to divide both sides by this. So on the right, we already had x times this quantity, negative 2x squared minus y squared. Now we're going to divide both sides by this, and at the same time, I'm going to factor out a y. So I'm going to factor out a y, and then left in here is going to be x squared minus 1. So there's our derivative. Y prime equals this in terms of x and y. And again, I should have pointed out, I forgot to, when we took the original derivative of this, remember we distributed the x squared and then we took the derivative. As soon as we had that raw derivative, we could have plugged this point in. And we could have found the slope, m, and we already had the given point, and we could have found our tangent line there. But, here is our derivative, all nice and simplified with all that beautiful algebra to get us there. Now we can plug in the given point and find the slope. And I really like this point, the square root of 2 over 2, comma, the square root of 2 over 2, because wherever you see an x or a y, that's what we plug in. And we'll start here. Here's our numerator. This x is the square root of 2 over 2. And then in the parentheses, minus 2, and then we have that quantity. Square root of 2 over 2 quantity squared for this x, minus the square root of 2 over 2, that quantity squared for this y. In the denominator, now we have this leading y here. That's a square root of 2 over 2. And then in our parentheses, x squared is square root of 2 over 2, that quantity squared, minus 1. Now, before you get overwhelmed by all these square roots of 2 over 2 and whatnot, before we distribute or square anything, there is something that's going to cancel real nice. Our derivative, the leading term of the numerator was an x, the leading term of the denominator was a y. They were both plugged in with square roots of 2 over 2, so those are going to cancel right out. We don't have to worry about distributing those at any point. So back to the numerator, here is our negative 2. Square root of 2 over 2 quantity squared. Well, the square root of 2 squared is 2 over 2 squared is 4. 2 over 4 becomes a half. So that's negative 2 times a half minus this square root of 2 over 2 quantity squared also turns into a 1/2. All over, down here in these bottom set of parentheses, root 2 over 2 quantity squared is still a half, and we have our minus 1. So, let's see here. Negative 2 times a half is negative 1 minus a half, all divided by, down here in the denominator, a half minus 1 is negative 1/2. I'm sort of running out of room. We'll come back over this way, I guess. 1 minus 1/2 is negative 3/2, and that's divided by negative 1/2. So a fraction divided by a fraction, invert and multiply, 2 over 1 negative. The negative times negative will cancel, and when we multiply across here on the diagonal, we'll get those 2's to cancel. We're left with 3. dy dx, our slope, our instantaneous rate of change, all that work for a nice easy 3. Again, now that's just about the last piece to our puzzle. We needed a slope and a point, because the original directions were to find the tangent line. So, m equals 3. Our point is root 2 over 2, comma, root 2 over 2. Okay, plug that into the equation. Y minus y sub 1 equals m times quantity x minus x sub 1. So here on the left, we're going to have y minus the root of 2 over 2. And that's equal to m, our slope was 3, times the quantity, x minus the root of 2 over 2. We'll distribute the 3, and we'll add this to both sides. So let's see, here on the right-hand side, we're going to have a 3x minus 3 square roots of 2 over 2. Here on this side, this was a negative root 2 over 2. We're going to add that to both sides. So now this will be a plus square root of 2 over 2 over here, just leaving the y equals. Y equals. Okay, here we can combine these. We have our 3x, negative 3 root 2 plus positive 1 root 2, those are all over 2, becomes a minus 2 square roots of 2 over 2, and these leading 2's will cancel out. So we're just left with y equals 3x minus the square root of 2. Y equals 3x minus the root of 2. That is the tangent line at this point. We had the point that was given in the problem. We had to find the slope. The slope was positive 3, pretty steep slope there. So what we found is the equation of that light blue tangent line right there, and put it in y equals mx plus b form. And if I'm not mistaken, that's the last example in implicit differentiation. That's it.